Hello and welcome once again for another episode of Profiles in American Funded Research. I'm excited to have my guest today, Berardo Matalucci. Berardo studied at the Universidad Politécnica de Madrid, got a master's at the Institute for Advanced Architecture of Catalonia, and got his PhD here at Rensselaer Polytechnic Institute. So right, not too far from where I am. Um, and he is now the co-founder and CEO of Mimic Systems. And I invited him on today to discuss this project, which is entitled Refrigerant-Free Heat Pump Using High-Performance Thermoelectric Materials and Methods. So I'm excited to have you on, and I would just like to give you a few minutes to first discuss, a general overview of the project, and then we'll go from there.
Well, Jeremy, this is a wonderful opportunity for me, actually, to share some of the work that we are doing. Uh, just out of quick clarification, most of my background is when I studied was in Italy. I only spent few years, a few months in Madrid, and then moved to
Okay.
Barcelona, just out of clarity. You never know. Just wanted to clarify. But the reality is that all through my career and my journey and my studies and even my professional work, I've always been fascinated by the topic of heating and cooling and how it relates with building technologies and how somehow building technologies could or should do maybe a better job at delivering the right amount of comfort to the people, but at the same time, making sure that there are no um, challenges to either the environment or topics related with the issue or maintenance or general economics of how heating and cooling is performed. And so the nature of the work that we've been lucky and to be honored enough to receive funding from the National Science Foundation focuses on removing a critical or replacing a critical component in traditional heating and cooling systems, which is the compressor and the use of refrigerants. So whenever we have a typical air conditioner or window unit or a portable system or even our rooftop mounted unit, inside there are big compressors, smaller big compressors that use refrigerants. Now there's been a lot of innovation in making sure that the refrigerants are super efficient, but at the same time trying to minimize the environmental impact or the toxicity of some of those refrigerants. The reality is that we want to take a different look at it. What if we don't have a compressor? What if we don't have refrigerants? And the way that we do that is through the National Science Foundation primarily is by uh, developing a new class of materials and fabrication methods through our academic partner to develop a solution that is fundamentally based on solid state technology, meaning that does not have any moving parts, and it uses semiconductors to make hot or cold in very simple terms. And this is what is the goal of the work funded by the National Science Foundation, really developing new fabrication methods and new materials that can enable us to reach parity or superiority when it comes to efficiency against traditional systems.
Thank you very much for that introduction. So, one of the things that I'm interested in, I want to get more into the details of what you're doing. Obviously, not too far to make it so that you can't commercialize it yourself or anything like that, but just high level. But I did want to just briefly discuss the SBIR, which is what this grant was funded under. I've actually talked to several people who had no clue that this program existed. I was familiar with it actually for some reason. I don't know why I was familiar with it, but I was familiar with it from before. But I know a lot of people don't know about this, and it's the Small Business Innovation Research part of the NSF. Can you just discuss like why is this program there, and what makes it sort of essential?
Well, it's a wonderful opportunity too for small companies, startups like ourselves, or in general, small businesses, to be able to conduct fundamental research that otherwise would be very difficult to make it happen. Now, imagine that us as a small startup entity, we rely on a different type of source of funding to accelerate commercialization of new ideas or new products. But at the same time, it's important that we have a very solid and robust roadmap to be competitive even after the initial commercialization in the long run. And so what the SBIR effectively, particularly from the National Science Foundation, is effectively enabling us to do that, because we have now the opportunity to receive, I mean, we got the opportunity to receive funding and as such money to conduct basic fundamental research that enable us to solve very complex problems that could, in parallel, enable us to be more competitive in the future as we keep advancing our commercialization of our first product.
Yeah, I see this as like the thing that's going to touch people's lives most quickly out of anything that's funded by the NSF. I feel like this is something because you're actually in the stages of commercializing a product that will be used in the near future, whereas a lot of the scientific advances tend to be years and years off from the public. So I think it's a really important program.
It is, and to be honest, we are very proud of. And the reality is that even during the application process, one of the criteria was specifically focused on commercialization and commercialization roadmap or even traction. So the NSF is probably like other institutions that are funding SBIR, but at least from our experience, the NSF was analyzed our proposal through the lenses of the scientific rigor, how solid is the science behind what we would like to propose, how new it is, but at the same time, how successful as a company, if funded, we could be. And so in terms of commercialization. So they're really looking at those two things at the same time. And finally, they want to have a very broad impact. So they want to be as very innovative in the scientific field. They want us to be very successful and very quick in the commercialization roadmap and traction. And at the same time, they want us to develop something that is meaningful for society at large. And so it's a great opportunity to be part of. It's very challenging for us, but I mean, but at the same time, extremely rewarding.
So now I do want to get into diving in a little more into the science now, because I actually find this topic really fascinating. So whenever I think of say a refrigerator or of an air conditioning unit or even a heat pump, I always think of it in terms of refrigerants, right? Some kind of working fluid. I mean, I guess potentially you could use water, but it's not going to be as useful to you as these refrigerants and whatnot. So how are you getting rid of the refrigerant?
So refrigerants are, the principle behind refrigerants is actually quite fascinating, because you have those different temperatures that are associated with the transition between vapor and gas and liquid. And you're able to extract heat or remove heat. But there are other ways that you can accomplish that. For example, there are many different types of heat pump systems, or even non-vapor compression systems. For example, there is magnetocaloric that is using a magnetic field to generate heating or cooling. There are ion calorics that are using ions. There are elastocalorics that are using the deformation of certain materials. And then from our end, there are thermoelectric materials. Effectively, the physical phenomenon, it could be described maybe in simple terms as the coupled electrical and thermal transport through solid state matter. It means that when you have a solid and you apply electrical field, electricity will move on a certain direction, for example, from the top to from the bottom to the top. And as electricity moves in certain types of materials, you also have an associated transport of heat, meaning that heat will move from the bottom to the top, or vice versa. And that means that the bottom surface will become cold and the hot surface will become warmer. If you reverse the polarity, if you reverse the directionality of the electricity, you are able to do the opposite effect. And so this is for us, it's absolutely fascinating because now we can use solid materials and simply use electricity as a medium to make something warmer or colder. From a high level principle, it's from a concept perspective, it's fascinating, and it has been around for a while. The literature or the scientific knowledge, they either refer it to Seebeck effect or Peltier effect, depending on how you consider those stuff. But the reality is that the challenge from our end is try to make this physical phenomenon as efficient as possible from an engineering perspective. And so that is where a lot of the work has been done so far.
Now, does that involve, I imagine that involves a number of different optimizations that are going on, but so does that all like is one of the things that you're looking at, like the choice of the material for solid state, you know, silicon versus other things that can be put in that are solid state materials?
Yes. So the reality is that there has been a lot of funding that have been poured, a lot of resources and funding that have been deployed to make better materials when it comes to this type of thermoelectric devices. And and none of, probably very few of them were able to yield very significant or significant improvement. The reality is that when you look at thermoelectric effect, it's very important to have a system that is well designed because there are so-called parasitic losses or inefficiencies when you put together a system or a unit, a working unit, that you have to be very mindful of, because if you don't treat them in the right way, basically all your efficiency can be degraded very quickly. And also they require certain types of power electronics or control boards in order to operate them at their best efficiency. So there are already two layers of optimizations that we were able to bring in. One from the system design, the way that you put together different subcomponents or parts, and the other one from the power electronics and controls. That is really important. But then the last piece is how do we make the materials as best as you can? How do you improve the efficiency of the materials? How do you make them cheap and available for mass adoption? And that is something that, for us is of paramount importance. And this is something that this is primarily funded by the National Science Foundation.
Yeah, I see. So yeah, you also have to take it. You can't just find the best materials and that's it. You also have to consider cost because you're trying to sell this thing
Yes.
eventually. So cost becomes important as well.
Yes,
Oh,
very important.
um, this is not always something we think about in the scientific community. Sometimes we don't worry about about those things, but you're at the forefront of this. So
I mean, it is a very sensitive topic. You know, it's important that as a company we outline our product development in a way that matches our technical development. So we can start with certain types of product applications where perhaps, at the end for the beginning, maybe some sort of premium could be tolerated, could be acceptable. But the reality is that when we look at mass adoption of heating and cooling systems, the regular homes, the regular inhabitants, the regular people that live everyday life, we have to be cost competitive and we have to be very cost sensitive. And this is something that, again, the work that you're doing, funded by the NSF, is important because it will lay down the ground field, the work for us to become cost competitive, because we are able to build up all this kind of innovation in materials, fabrication processes, and ultimately bring down the cost.
Now the thermoelectric devices, can they be competitive in terms of, say, the efficiency of power usage? Uh, can they be competitive with uh, the compressors that are using refrigerants?
For some applications today, yes, they can be. Um, it's a it's a tricky balance, because in general, thermoelectric systems, they operate slightly different than a typical compressor. Unless you don't get very sophisticated, if you get very simple basic compressors, thermoelectrics, they tend to operate best at when the temperature are not extreme, temperature differentials are not extremes, whether sometimes typical compressors, entry-level general compressors, they tend to be operated at their best in certain extreme warm conditions. Um, the reality is that when you look at the energy consumption throughout a year, in some applications, the current devices or current thermoelectric technologies can be as efficient or sometimes even more efficient than traditional vapor compression systems. Now, as we keep innovating in materials, as we keep making our system better, or even maybe as we couple uh, our system approach with something else, like a backup compressor system or something, natural refrigerant system, we can achieve efficiencies that could be significant, could be very, very high. And so this is unlocks for us the opportunity to innovate significantly in the space of heating and cooling.
And it seems like, I may correct me if I'm wrong, but it seems like this kind of system might actually be able to be smaller than a traditional heat pump in physical size, because you need the compressor and the working fluid in that case, and it seems if you remove that, it almost feels like it would be smaller.
It has the possibility to be smaller. As a startup company at the early stage, we, even in our product development, we are building a lot of redundancy in the system. So it's even looking at our initial prototypes, they feel bulky. But because we haven't done a significant optimizations in the form factors or the economy of those materials, again, we are early stage, and that is, we want to build some redundancy and be a little bit conservative. But the reality is that you have the opportunity to make them smaller. But not only just that, it's you have the opportunity to also make them modular. So meaning that if you have now a small living room, or if you have now a small bedroom, or a large living room, or a small bedroom, you can tailor the capacity really to what you need. And so the system grows or reduces depending on the system, the form factor grows or reduces depending on the real capacity that you need. And that could be a significant advantage because you have now opportunities to integrate maybe something else, or a battery pack, or system for better ventilation or better filtration, or simply have a very different form factor depending on where it's located.
Yeah, I can understand, going back to you were discussing the redundancy. I imagine that you probably need some kind of redundancy because you want things also to be reliable. So you don't want these things breaking down constantly or anything like that. But this modular idea sounds amazing to me. So it almost feels like potentially in the future, maybe you might be able to have sort of a micro control over the climate, right? Like some kind of,
Yes.
yeah.
That is one of the things that, to be honest, fascinates me the most, is the ability to for the product to be somehow customized according to different type of spaces and different type of applications. Even in a typical living room or a typical dwelling, you could have the opportunity to distribute different modules or different units, and thereby controlling the climate or controlling the microclimates of every dwelling. Or even if you look at an office space or a retail space, you have the opportunity to create those microzones where, first of all, you can capitalize on efficiency in a different way, because then you can turn on and off only areas where people are occupying. And so you can capitalize a lot in efficiency where you don't deliver heating or cooling if nobody is occupying that space. But also you can meet different demands from different people. Generally in typical office spaces, making sure that everybody is comfortable, it's a it's a it's a big topic. Some people feel warm, some others they feel cold, and it's always a struggle who controls the thermostat.
Yes.
But with this kind of mentality, you have the ability to actually distribute the source of heating and cooling, and thereby providing better quality for people, better experience.
I am totally familiar with this because, my wife and I have essentially different internal thermostats. So one is hot and the other is cold. This is a problem frequently we run into.
And and to be honest, it's one of the wonderful things about technology, right? Isn't it? Because they enable to solve the problem through a different type of lenses, from a different perspective. Uh, and it's totally fine that people have a different set of preferences, depends on their a variety of different factors: gender, age, background, culture, and so on and so forth. It's totally fine. Uh, but the reality is that how do we develop a technological solution that can enable to meet personalized preferences? And so that is what for me is fascinating about this.
Now, I know that you probably obviously as a business person you're going to want to target as wide of an audience as possible. But in the initial stages here, are you thinking more that you're going to target more individuals like homes and things like that, or are you going to target the businesses first, bigger buildings and things like this?
One, uh, one opportunity that we see very dear and very close to where we operate is retrofitting of or electrification of light commercial buildings, and there is a class of those buildings. Typically seven stories and above, taller buildings. Could be either light offices, light commercial offices, or high-rise multifamilies. Generally, the challenges associated to moving to all-electric heating and cooling that is associated with amount of work that you have to do to upgrade all the systems. You have to physically enter into the units, and you have to do a lot of labor, open up walls, and do all this kind of work. One of the embodiment of one of the product solution that we are developing actually is directly could directly solve this problem by providing a very simple drop-in and replacement for that could replace the incumbent solutions like a radiator, like a fan coil, which would be very simple from a property owner and from a property management perspective. Very simple. You can do it incrementally as people move in and out. You can do it so you don't have to have a lot of capex, a lot of capital requirement at the beginning. You can dilute over a certain amount of years. And when the building is ready, you can actually operate it extremely efficiently. That is for us is an opportunity that from a commercial perspective makes a lot of sense. But the reality to get started with, to enter the market, and this is again going back to the NSF, they during the application and the SBIR program, they are very interested in this kind of approaches because they want to make sure that companies are thought about the science, but also how the science can be applicable very quickly. But that doesn't mean that in a few years we won't be able to reach larger adoption, single family homes or different type of products. It is that we just have to be careful in the way that we uh, roadmap or plan the first initial products.
Yeah, absolutely. I think I can see that planning is very important. So you want to gradually get yourself. You don't want to have your hand in too many baskets at once. It's got to be kind of a focused, especially for a new business, a focused approach.
Yeah, very much.
Now, I noticed in the description for the for this grant that you discussed also printable electronics. So are you thinking, you're going to be able to 3D print these some of these electronics or something like that, something along those lines to put into your product?
So some of the innovation that we are baking into this part of this SBIR work is taking inspiration from the way that new electronics or new printed circuit boards, PCBs, are actually started to get manufactured now for high high heat applications, for example, for LEDs or other systems that require to manage a lot of heat. And so we're taking that inspiration because it's a very scalable process. It uses additive manufacturing or printing techniques to basically set an array of different type of semiconductors or chips in different places. And this is very similar or akin to what we could potentially do with thermoelectrics. And so the reality is that for us, it's a wonderful opportunity because first of all, it's a scalable system, and secondly, it's very flexible in terms of our ability to customize for our application. The reality is that who knows, maybe in the future we could integrate our electronics board directly or very close to our thermoelectric boards, and so streamline the manufacturing process, unifying it. It's certainly an opportunity that we haven't fully developed, but it's certainly around the corner, or very, very, very feasible.
Yeah, I can see lots of advantages that might come from something like that because I mean, I'm just thinking like inevitably always something needs to be repaired or something like that. So you could on demand rather than having to have pre-produced a bunch of these things, you could just print them as needed for repairs or when you need to make a new product or something like that.
It's actually also opening up the opportunity for distributed manufacturing. So, and I think this is something that we are a little bit early for a complete evaluation, but the reality is that you could potentially leverage resources that are already in place in many places in different parts of the world for us to use the technology, but rely on service manufacturers or contract manufacturers or somebody who can basically print them for us rather than having us to be invest in a lot of manufacturing. So there are opportunities to explore this kind of hybrid models where we could have distributed manufacturing where they are close to where the products are deployed rather than shipping back and forth.
Yeah, that sounds like just another way of increasing efficiency, right?
Yes.
The efficiency from many different angles. So now, how easy do you think it's going to be to sort of scale this up? So initially you get a couple of customers. It sounds like maybe potentially this might play a part of that, a role in that, right? The being able to print things. But how easy is it going to be able to go from I know it's just I'm just asking you to speculate here. Obviously, you haven't you haven't hit that part of the road yet, but uh, to go from, your first customer to your 100th or whatever, how easy do you think that's going to be to scale?
Oh, it's one of those questions where I could respond using two parts of the brain. The first one is the very naive one, and I would say it's super easy because the processes that we are trying to build up are meant to be scalable. But the reality is that I don't think it will be so easy. It's dealing with hardware, dealing with physical products. It has complexities that are true and valid everywhere. It's a matter of managing the supply chain. It's a matter of having, you know, machinery, equipment, or even a contract manufacturer or a set of contract manufacturers. Uh, it's challenging. I don't want to be so naive to say that it's around the corner and it will be super easy, because it isn't. We were able now to assemble a handful of prototypes, and yet it's a convoluted process to do it the first times. So there will have to be investments to make sure that we are able to grow and we are able to scale relatively easily, or for as much as it can be. And this is one of the also other things, and maybe could be a leadway. It's one of the other things why, for example, this SBIR proposal is staged into two phases. So there is a phase one and then there is a phase two. And the reality is that the NSF realizes, like many other institutions with the SBIR grants, that it's difficult to scale up. No matter where you are. And so that they structure a proposal with a phase one, giving you a little bit of money and resources to make sure that from a proof of concept perspective, your idea or your company's idea, your vision has legs from a scientific perspective and from a business perspective. And then if successful, the goal is for us to try to see if we can get a phase two proposal where there is a larger pool of money that are actually would be dedicated for enabling growth, enabling the ability to scale and grow.
And how, so how long are these phases? Phase one and then potentially phase two. How long do they allow you to, stretch out the use of the funds?
So typically, phase one tends to be between 6 and 12 months, if I'm not mistaken. Um, and phase two, I think, could be maybe wrong at this point. I didn't double check, but maybe 18 months, a year and a half, maybe 2 years, give or take.
Yeah, I see. So they really want you to hit the ground running and get these products to market fast.
It's um, it's incredibly fast. Yes, it's fast.
So of course the purpose of this podcast is not only to introduce the science and things, but also to let people know where that money is going. So for you, I know that you obviously you're investing in materials, but where else is that money going? What else is it going to?
You mean from the National Science Foundation?
Yes, yes.
The what is the way? So the National Science Foundation in general and typically SBIR proposals allows people to have the ability to have a couple of different partners that you can bring into the table when it comes to setting up the scope of work for a project. In our case, for example, we decided to allocate a significant amount of funds for the company, investing in materials and paying engineers to develop this kind of research. But also we decided to collaborate with a university partner that are doing very good work groundbreaking work on the new materials. And so the goal is to actually have universities and academia to directly feed into the work that we are doing so that we can accelerate, but at the same time, we can tap from some of the research that is already going in the university and accelerate that.
So you're partnered with the university. Are you also partnered with any other business partners, or it's just you and the university?
For this specific grant, we partnered with the University of Notre Dame, and we decided not to have other additional partners. But again, from a funding perspective, as long as there are minimal budgeting allocations, you have the ability to have even multiple partners. So there is flexibility from organizational perspective.
And I know I mentioned at the very beginning of the podcast that you are a co-founder. So are you two the only two employees of the company at the moment? I know that you're probably contracting out because you mentioned engineers and stuff, but are you the only two official employees?
So I am full-time in the company. My co-founder is a professor at a university, started the company with me, and is a significant part in making sure that we are able to, stay on track when it comes to science uh, and scientific rigor. Plus, we have two two wonderful full-time employee and a wonderful part-time chief innovation officer, and plus so those are the core items and plus the core figures. Plus we also have a wonderful chief technology officer in the company.
Very nice. So your two full-timers, what kind of role are they in?
One of one of them is is our first hire. Is actually a physicist. His background is in physics, with strong expertise in electronics and electrical systems. And I think it's a wonderful balance because he understands the nuances of the technology from a physics perspective, from a core physics perspective, but it's also very skilled in outlining all the different sensors and components, power electronics, which I am not, clearly. Really able to make those things happen. And the other employee is a mechanical engineer who is very skilled with 3D modeling and assembling stuff. So it's and simulations. And again, it's a really delicate balance when it comes to talent that you have to consider for startups.
So you've assembled a good team then.
Oh yeah, we have a fantastic team.
So my last question, which I always is something that I'm personally interested in, and I typically ask this on the podcast, so so you'll have to bear with me. But what got you interested in science in general? Because you obviously you understand the need for the science and to build your company, but what got you interested in science?
So I built my career around technology and sustainability when it comes to the built environment. So I was lucky and fortunate enough to work in Italy, where I'm from, in Europe, and coming in the U.S. I came to New York and started to again working on the field of construction and buildings. And at some point, I met a couple of wonderful people who were running what's called the Center for Architectural Science and Ecology case. Um, I was blown away by what they were doing. They were really reimagining the role of technologies for buildings. And at the time, I was only looking at how design could improve the experience of people uh, in buildings, but they had a completely different look at how technologies could really revolutionize the, the experience and the whole dynamics in the built environment. So, quit my job, and I decided to do a PhD with them under their advisory, and that's how everything started. And as I kept diving into it, I then went to work for a firm in New York, design firm, where I was honored and fortunate enough to work on super cool projects, very huge, big scale, big clients. And again, I was leading all the sustainability and environmental technologies and design aspects. And again, I learned how complex from an implementation perspective is to inject new technologies into the traditional way of buildings or designing buildings. And 2 years ago, I think I just realized that it was time for me to make a contribution in the field, and I resigned, and this is where I am.
Here you are. Well, thank you very much. I greatly appreciate having you on the show, so that we can show the wide variety of projects that the NSF funds. So thank you for coming.
Thank you, Jeremy. My pleasure.